So we're looking at page 12 of the Unit P packet. We're talking about classical curves specifically related to polar functions. And so these curves are really important because if there is a way to model them using ordinary function notation, it's not the kind of notation that you would expect to be able to put in explicit form, y solved as a variable in terms of x, right? Or at least not easily. Right? So if you look at the structure of these models at the top, they're not overly complicated. R equals a plus a cosine theta, for example, for a cardioid. Right? Not complicated, but its function analog is very complicated. Right? So we want to be able to handle these kind of curves without having to go into rectangular form. All right? So what we're going to do is make a table of values. So we're going to go back to trig class here. All right? So we have an independent variable, which is theta, and we have a dependent variable, which is r. And what we want to do is we want to grab convenient values for theta. All right? And so that's the tricky question. And I've gone through entire lessons related to this where people would patiently wait and listen while I go through the whole rigmarole and spiel, and at the end say, okay, I understood everything, except how do you know what values are convenient for theta? So if you go to the end of the packet, you'll see a nice little unit circle here. So convenient for the cosine of theta would be any value that is on the unit circle, right? And convenience is kind of a relative term. So since cosine is your x value for any coordinate, cosine of theta, and sine is the y value, I'll use a little highlighter action here. Every one of these values here, and as painstaking as this is, kind of like, are we really doing this? Yeah, I'm really highlighting every single value along the unit circle that is in the x position. All right? Those are all cosines for the corresponding angles. So 30, 40, so 0, starting with 0, 30, 45, 60, 90, and so on. Right? So then the question would be, well, what makes an angle convenient for cosine? So I would kind of trim this even further and say, well, I guess any one that doesn't involve a radical. So I got this one, this one, this one, this one. I could keep saying this one, but you get the idea. All right, any angle that gives a cosine value that does not involve a radical. Right? Now, is that always going to be the most convenient case? Well, not necessarily. If part of the expression is a radical, then maybe that would offset it in some way. That's the part of the number sense component of things that we need to kind of nail down. But for the most part, we're looking at quadrantals and 60-degree reference angles. Now, you would be forgiven if you didn't know what quadrantals meant, because honestly, I didn't know what that meant when I was a student. It was one of the first terms that I fell in love with when I was a teacher. Fell in love with is strong. It's just, I learned the term, and then I've never stopped saying it ever since. Quadrantals are the angles that fall on an axis. All right, so I know I've mentioned that a few times. I don't know that I've ever actually explicitly stated what they meant. All right, so if I didn't know what it was as a student, I don't know that I would expect other people to either. All right, so quadrantals or 60-degree reference angles. Now, the 60-degree reference angles, that's something you dang well better know. All right, 60-degree reference angles. And if not, it doesn't mean drop the class. It means, well, study it. Get to know it soon. Toot sweet. Very, very important. Right? And if I can get some feedback from previous students, and I'm sure I can dig through my emails and all that, but I can promise you they're all saying the same thing. If I only knew my trig, I would do better, or thank God I knew my trig because I did so well because of it. And it's one of those two things. All right, so if we're working around the circle, starting at 0, then going to, it's up to you. I mean, there was no direction except to graph, and the grid itself is given with degrees and radians. So if you like degrees, go with degrees. If you like radians, go with radians. I'm going to go with radians. So pi over 3, and I should make a note, same as pi over 3 reference angle. All right, so pi over 2, 2 pi over 3, pi, 4 pi over 3, 3 pi over 2, 5 pi over 3, and 2 pi. All right, that's one full turn. If we need more, then we'll get more. All right. So now it's a question of, all right, well, what do we want to do? Do we want to do all this by hand, or do we want to do it in our head, or do we want to go to a calculator? In my class, there's no wrong answer to that. It's not a trick question. It's, well, which one do you want to do? Like, if you're weak in your trig, then you can't do it in your head, or it's harder to do in your head. So do it in a calculator. Right? If you're strong in trig, then maybe you've already got it figured out before you would even have, it would take longer for you to type it into a calculator. So let's pop in the 0 for cosine. Cosine of 0 is equal to a 1. 3 times 1 is 3, plus 3 is equal to 6. All right. Pop in a pi over 3, and we're looking at 1/2. 3 times 1/2 is 3/2, which is the same as 1.5, so this is going to be 4.5. So 4.5 or 4.5, either way. We got to estimate the points, that's why I'm going to mixed numbers or decimals. All right, cosine of pi over 2 is 0, so this becomes a 3. 3 plus 0. 2 pi over 3 is equal to a negative 1/2, so it's really 3 minus 1.5, because negative 1/2 times 3 is negative 3/2, so negative 1.5. So 3 minus 1/2, 3 minus 1.5 is going to be 1.5. Pi is negative 1 for cosine, so 3 plus 3 times negative 1, so 3 minus 3 is 0. 4 pi over 3 has the same cosine value as 2 pi over 3, so you should get the same answer as 2 pi over 3. 3 pi over 2 has the same cosine value as pi over 2, so you should get the same answer there. 5 pi over 3 has the same cosine value as pi over 3, so you should get the same answer there. And 2 pi has the same cosine value as 0, so you should get the same answer there. All right. Now, if you needed to pop this into your calculator, you have all these values. You could do it one way or the other. One way would be to make a table of values. The other way is to just do plugging and chugging. If you're going to do plugging and chugging, what I would recommend is put in a constant. So 3 plus 3 cosine of, let's say, A. Introduce a slider for A, and then pop in your values as an A. I find that to be easier. Maybe you disagree, but you'll try it in a different way if you disagree, and you'll see, and then you'll make your decision from there. So 2 gives you a 3, so the values up here under the 3 plus 3 cosine A is what you get for your answer. All right, so 3 and then 2 pi over 3. So a little tap there. A 3, 1.5. You get the idea. All right, so now what we need to do is plot these points. But remember, points are plotted in the form of r comma theta. All right, which is weird because we write them in the form of r comma theta, but we kind of think of it theta first. So the table kind of gives us a better clue as to how we should plot it. But the way we should represent our answers, our coordinates, I should say, would be the r's first, then the theta. It's very strange. smidge that up a little bit. So like this. It would actually seem in a lot of ways to be more appropriate to identify the coordinates as theta comma r, and some people do. Those rebels. Actually, I think they're probably justified in their decision. So I don't know if that fits the classic definition of rebellion. Or maybe that does fit the classic definition of rebellion. So what we're going to do now is plot these points. So 6 steps in the direction of 0. We're going to go off the grid a little bit, but that's okay. All right, so 1, 2, 3, 4, 5. I'll ballpark 6 to be about right there, because everything except for the 6 is going to stay on the grid. So 4.5 in the direction of pi over 3. So 1, 2, 3, 4.5. 3 steps in the direction of pi over 2. 1.5 steps in the direction. So 1.5 steps in the direction of 2 pi over 3. No steps in the direction of pi, so that's back of the pole. So I can actually get this part of the curve. 1.5 steps in the direction of 4 pi over 3. 3 steps in the direction of 3 pi over 2. 4.5 in the direction of 5 pi over 3. And then back to 6 steps in the direction of 2 pi. And so this would be your curve. Oh, a little miss at the end there. And actually I kind of went wide initially. Oh, that's a little iffy, but make the points a little bigger and you're good. Yeah, so you get a little sideways heart there, which actually makes sense because what we just graphed is a cardioid. Cardioid, cardiac, heart. Now, is it as picture perfect as this baby right here? I wouldn't say so, but it doesn't look so bad for a freehand drawing. All right. So the next example, you kind of streamline the process a little bit based on what you liked from my first demonstration and what you disliked. You said, well, I'm not doing that again. Or you say, well, I'm going to do exactly that again because it worked for me. So we still have this piece of information, except now it's not for or related to a cosine function. It's going to be related to a sine function. So will this 60 degree and pi over 3 apply anymore? I would think probably not. So let's take a look at our unit circle again. For the sine function, it's the y values in the coordinate. The convenient ones, again, we're looking for the y values. The convenient ones would be the ones that do not involve the radicals. So we're looking at basically any denominator. If you're looking at the radian form of an angle, any denominator that involves a 6. So pi over 6 30-degree reference angles. All right, so that's something. That's something good. So we know we're dealing with 30-degree reference angles, or pi over 6 degree reference angles, pi over 6 radians as your reference angle. All right. So I can do my table thing again. There'll be some modifications. Particularly any denominator of 3 goes to a 6. We'll have to change some numerators along the way too. All right, so pi over 6, 5 pi over 6, 7 pi over 6. Oh, that's not the one. And 11 pi over 6. All right. Now each one of these values is still going to give us a 1/2 in some capacity, whether it's 1/2 or negative 1/2 for the non-quadrantal ones. All right. 0 gives you a 0, so that's a 4. Pi over 6 gives you a 1/2. Negative 4 times a 1/2 would be -2. So 4 minus 2 is 2. Sine of pi over 2 is equal to 1, so 4 minus 4 is 0. 5 pi over 6 is a 1/2, so same answer as the pi over 6, so 2. Pi gives you 0, so same answer as 0, and that'll actually be the same answer as 2 pi. 7 pi over 6 gives you a negative 1/2, so 4 minus 4 actually becomes, 4 minus 2 becomes 4 plus 2, so 6. All right, because we're taking that negative 4, multiplying it by a negative 1/2, so that becomes a positive 2. And that's going to be the same thing for 11 pi over 6. 3 pi over 2 is a negative 1. Negative 4 times negative 1 is 4. 4 plus 4 is 8. All right, so we're going to do the same thing that we did before. We're going to get these coordinates. I'm going to try to sneakily take the framework here. And I think I grabbed the 4 along for the ride. I might have to adjust that. Oh no, it'll work. Now, do you have to write all these coordinates down if you have an intuitive understanding? I would say probably not, but I'm doing it just so you have it. You know, it's taking an extra couple of seconds, but you know, I think it's a worthwhile use of the time just so you have it in the proper form. All right. So we're looking at 0 radians, 4 steps in that direction. 2 steps in the direction of pi over 6. 0 steps in the direction of pi over 2, so that's back at the pole. 2 steps in the direction of 5 pi over 6. 4 steps in the direction of pi. 6 steps in the direction of 7 pi over 6. That's going to put us off the grid a little bit, like somewhere around there. All right, that's the same thing that's going to happen at 11 pi over 6. I'm just going to pop that in there. All right, 8 steps in the direction of 11 pi, 3 pi over 2. So that's a little lengthier. So let's say 6, 7. Well, it's going to be somewhere around down here. And maybe a little shorter. It's all right to ballpark. What's not all right is my drawing ability. Oh boy. All right, that's the best I got. Now, you could use that computational approach that I showed before. Now, something else to keep in mind, I've kind of glossed over this. There is the function, the polar function, in your Desmos. You know, just by tapping on the little wrench there, you have rectangular mode and you have the polar form, right? So if you do that, if you set it in that mode, you know, and go to, you know, whatever zoom you think is appropriate. I'll do a zoom default. Then you could type in your original function, which would be r equals, it understands r, 4 minus 4, this one was sine. But then you have to type in the word theta, not theta, theta. It understands theta once you type it in. On the whatever the domain ought to be, in this case 0 to 2 pi is what the default is, and so that's what I left it as, because that seemed to make sense to give us one full loop. All right. So So yeah, that's what the graph should have looked like. Not quite what I came up with, but